Welcome back. Today we will be covering Roman numeral 4 on the basics of current electricity. Remember, we are going to be doing labs and example problems together in class, so this video's purpose is for you to get down the equation so that we can get up and running whenever I see you next time. So let's get started. Letter A is on electric current. The variable used for current is a capital I, and its definition is a flow of charged particles. Now our equation we're going to use for current, again, capital I is current, lowercase q stands for a charge, and then we're going to divide by time. So we're thinking of that as a type of rate, the rate at which the charges can flow. Our units are over here to the side. Charge is in coulombs, and then time is in seconds. A coulomb per second is given the nickname of an ampere or an amp, and it's abbreviated with a capital A. Now we are going to use a device like this in class, and that's going to be called an ammeter, and that's how we're going to measure our current. We are also going to be looking at these things called schematic diagrams. That's a fancy name for we're going to draw a picture of a circuit. Now each of these different devices that we have in our circuits can be represented by symbols. That way everything's going to look uniform and you can follow a diagram and be able to build a circuit in class. And that's what we're going to be working on together. But for now, you need to know that if we were to put an ammeter to measure our current in a circuit, we would draw that picture as a circle with a capital A on the inside of it. And then these two little lines represent the wires that are going to be attached right in here to our ammeter. Now there's no schematic diagram symbol for electric current. However, sometimes we'll see the direction indicated with arrows. And you should know that current is going to go from the positive end of a battery to the negative end of a battery. That's the direction of conventional flow. Next we have resistance. Its variable is a capital R, and resistance is a way to determine how much current will flow. We're going to use resistance in an equation later. It's called Ohm's Law, and we'll get to that. But for right now, you need to know that the unit for current is called an ohm, and it's abbreviated with that Greek letter, capital omega. Now, these are pictures of some different resistors that you're going to work with in class, and we're going to put those together in our circuits. You may want to find a site online where it talks about color coding resistors, because you're going to have to be able to read those color codes and look them up online. You don't have to memorize anything, you just need to know where to search and find those. Because each of these colors are going to represent a different amount, and that's how we'll know how much resistance is in each of these resistors. Now the schematic diagram, remember that's a fancy term for drawing a picture of a circuit. A resistor, one of these things, is going to be represented with a zigzag line, and you can do that horizontally or vertically. And you can think of the zigzag as it's creating some resistance for that current to travel through. It can't just flow straight through very easily. I have a joke for you, so you can pause and see if you can come up with the answer. If you can't, and you're really curious, I'll tell you in class. So next we're going to cover Ohm's Law, so I'll give you a couple of facts about that. And we are talking about the relationship between resistance, potential difference, and current. Potential difference right here is also referred to as the voltage, and this is going to be what comes from our battery. So Ohm's Law is going to give us a way to see how the voltage or potential difference is related to the resistance that's in a circuit and how well the current can flow through that circuit. The equation looks like this. Technically, our voltage, since it is a potential difference, we do write it with a delta sign, and that is referring to the potential difference from the positive end of the battery to the negative end. And that difference is what determines our voltage. Again, we're going to talk about that in class when we do our labs. But it's this voltage or potential difference that's equal to current times resistance. And then over to the side, I did our units. Voltage is in volts, current is in amps, and resistance is in ohms. And then I know you guys didn't need this, but I went ahead and already had the slide ready where Ohm's Law is rearranged for the different variables. And then if you would like to take a note, you can pause the video, and I just gave you a little bit more explanation about if things are directly or indirectly related. Now the way that we can tell how much potential difference or voltage is in a circuit, remember it's going to come from our battery, and this would be a voltmeter. That's how we're going to measure how much is provided from that battery. It looks just like an ammeter. What we're going to do is turn the dials. So we can use this for both an ammeter and a voltmeter, and then plug in our wires to the different spots down here when we get to our lab. If we're going to draw a schematic diagram, a voltmeter is a circle with a capital V on the inside. And again, these two little things represent the wires. Now, remember, a voltmeter, that's just a measurement of voltage, so we would get a numerical readout on the digital part of that voltmeter, but the actual voltage source is what's providing that voltage, and that's usually going to be our battery. And the way that we represent a battery would be one long line, that's the positive end of the battery, and one short line is the negative end of the battery. In our kits, we can go up to 4 batteries for the ones that we have. So just to kind of give you how that schematic diagram symbol would change, each battery that you have has a long and a short line, and we're always going to alternate positive and negative. On the plus and minus, the positive and negative end of the battery, you only need to label those on the very outside. So long and short is battery number 1, long and short battery number 2, long and short battery number 3. The long end is the positive end of the battery, and the short end is the negative end of the battery. And it is typical to draw the positive end on top and the negative end on the bottom. Now, to put these all together, we are going to draw some schematic diagrams in our labs, but I wanted to give you a couple of examples. So if I were to say I want you to draw a schematic diagram that has 2 batteries, a resistor, and an ammeter in it, I've got 2 examples like this. Now, there are a couple of rules, so I'm going to write those out for you, so pause the video if you need more time to write them down. First, we're going to have batteries, and only batteries are drawn on the left-hand side of a schematic diagram. Next, you'll notice that all the corners of our schematic diagrams are 90 degrees, and no elements, so no resistor, no light bulbs, no ammeters, nothing is drawn in the corner. So you're always going to have wires that represent the corners here. Now, if we have everything hooked together in one loop, this is going to be called a series circuit. Again, that's something we're going to go over in class. I'm just looking ahead a little bit. But if everything is drawn together in a loop, the actual order of things besides your battery, so our resistor and our ammeter in this case, they can be in any order, and they can be on any of the other 3 sides of our box. So here's another example. This time you have 3 batteries, so we have a long and a short for each of our batteries. The long end is the plus and the short end is the minus. You could have drawn your plus and minus on the outside. This just happens to be where I copied and pasted from that was on the left. The 2 light bulbs are a plain circle, and if they are lit, sometimes you'll see little light rays drawn out from each one. So that's an indicator that the bulb is actually lighting. And then our ammeter, remember, is an A with a circle in it. So again, only batteries go on the left. All the corners are right angles. You do not draw anything else in the corners. And then the order of everything else doesn't matter, and it can go on any side. So I could have put in, that's awful. Sorry. I could have put all 3 of my elements, 2 light bulbs and an ammeter, all in the same line. You don't have to spread them out, but it does look a little bit cleaner if you do. The last thing we're going to cover is electric power. And power does have units of watts like you see in a light bulb. So when we look at our formula and definition for power, we're going to look at the current that's traveling through a circuit times the voltage. So where does that voltage source or electric potential difference come from? We multiply those 2 things together to get our power. And I know it's kind of silly, but I remember this formula as poison ivy, because P and then IV. Just a little memory trick. You probably can memorize those a little bit better, but sometimes I need some help. Sometimes when we're given our circuit, we might know the current but not the voltage, or we might know the voltage and not the current. So we can use Ohm's law. Remember, it was V equals IR, and the delta is assumed, so I didn't keep writing the delta. We can substitute from Ohm's law into our power formula and come up with a few different ways to write power. So for example, if I don't know what the current is, I can take Ohm's law and solve for current and plug in V over R, and then when I multiply that out, I could say that power is V squared times R. I can also do the same by substituting in for my potential difference or my voltage. So I can substitute in IR, in for the V, And then when I multiply those two together, that's going to give me I squared R. So if you happen to not know the current or the voltage, you can use Ohm's law to substitute in and still be able to find the power. Now if we put all these together, we can say that power is equal to current times voltage, voltage squared over resistance, or current squared times resistance. And again, the units for power are going to be watts, which is a capital W. So I have one example problem for you. I think it's pretty simple enough, so we're going to go ahead and do this one together. You shouldn't have any questions about it. We are given a digital clock, and it has a resistance of 1.2 times 10 to the 4th ohms. It's plugged into a 115 volt outlet. So these are the variables that we know, and we're looking for the current. Remember, current is a capital I, so we want a formula that has current, resistance, and voltage in it. Hopefully you recognize that that's going to be Ohm's law. Again, the delta sign is implied, so you don't have to write that every time. And from this point, we should just be able to plug in and solve for our current. That is a really, really tiny current, so I did show you an equivalent in milliamps, so you didn't have all those zeros. Or you can change that to scientific notation. So it doesn't take very much current to make a clock run. Now for part B, we were asked to find the power. So remember, power typically was P equals IV. We could also, if you're not too confident in your answer for the current, we could have used V squared over R. That's an option for you, so you can do either one. But go ahead and plug that in and see what you get for the power and come back and check your answer. Okay, hopefully you were able to get about 1.1 watts. So it doesn't require very much power in order to run a digital clock either. So remember, these are the basics. We're going to work our way up to a little bit more complicated circuits, but we're going to be using Ohm's law, V equals IR, and power when we get to our other examples in class. And lastly, I have some jokes for you, so you can see if you can figure those out. If you're interested, ask me about them in class. I'm just going to leave these up for a couple of seconds each and see if you can laugh at them. Here's the next one. You can pause if you need a little bit more time to figure this out. We have a third one. And finally, our last riddle. That's it for today. Remember, if you did not get any of the riddles, or if you have questions from other parts of the notes, have your questions prepared and we can go over those first thing in class.